Hello, Year 12s. Alright, so today we are starting circular motion and gravitation. Now, I have the book open next to me, so we are going to go through pages 82 up until, what is it? 85. Okay, and then there are questions there, and then I will leave them for you to do come class time either tomorrow or later on in the week or whenever you have time. Alright, so the important information in your textbook is in that blue box at the beginning of each subchapter. So for circular motion and gravitation, an object moving in a circular path at a constant speed undergoes uniform circular motion. Uniform meaning that it is the same all the way around. Okay? This object undergoes centripetal acceleration, which is directed towards the center of the circle. Magnitude of the centripetal acceleration is constant for a given speed, and a radius is given by acceleration A, arrow on top, equals v squared over r. Okay? That is your first formula for this unit. Alright, next the formula. V equals 2 pi r over r relates speed to the period. Oh, I suppose it's over t, my bad. I'm wearing glasses and I still can't see. Relates the speed to the period of an object undergoing circular motion for the radius r. So, the other formula that you need is F equals ma. Okay? 3 formulas that you need for circular motion. These ones here. Alright, so like we did last time, let's break these down into their parts. A is acceleration, V is velocity, and R is radius. Okay, so there's our first one. Ta-da! Next, we have V is velocity. Yes, there's meant to be an arrow on top. 2 and pi are the same. They're constants. Well, pi is irrational, but we don't talk about that. R is radius, and T is period. Okay, and a period being how long it takes to do one rotation. Okay, and like it's a set length of time. Okay, how long it takes to do one rotation. Okay, now units for period is seconds. Radius is a measurement, so whatever the measurement is, whether that be meters, centimeters, kilometers, whatever. And velocity is meters per second, as per usual. Okay, and F equals ma. F is force, m is mass, and A is acceleration. Alright? So there's all those formulas broken down into their parts. Okay, there you go. Those are the 3 main formulas for this section of the course. Alright, so example question that we have there on page 82. The question is, calculate the speed of a cyclist that moves around a circular path of radius 2.2 meters in 1.7 seconds. So, first and foremost, figure out which equation you need. For this one, we are looking for the speed. So, we would do the V equals 2 pi r over t formula, because we have a radius, which is 2.2 meters. We have our period, which is our time, of 1.7 seconds, and 2 and pi are constant, and our velocity is unknown. Okay, so once again, when you're writing out your equations, seconds. When you're writing out your problems, write out what values you have and the unknown that you're trying to figure out. Alright, then we take our values and we plug them back into our equation. The V equals 2 times pi times 2.2 over 1.7. Stick that into your calculator, and that is 8.1 meters per second, which is a -1. Okay, that's that. That's basically how you go through that formula, trying to find unknown speed when you have the radius and the period. Alright, next, centripetal acceleration. So there is a diagram for this on page 83. So when you're asked to draw a centripetal acceleration, you draw a circle. You draw the various points on said circle. And now the speed is always at a tangent, and the acceleration always goes towards the center. Really should get a ruler to draw this. Okay. Okay. So if someone asks you to draw an diagram of centripetal acceleration, you draw this. Basically what you draw. So you have the motion going around, and you have different points on the diagram. You have the velocity going outside, so at a tangent to the motion of the object, and then you have the acceleration going into the center. Okay. Now this applies for uniform circular motion. So if we label it diagram of uniform centripetal acceleration. Okay, that is what this diagram is. Done. Okay, so we went through the formula. A equals v squared over r. Yes. Alright, so how do we use that formula? Look at example 1.39. So a test tube in an ultra centrifuge moves around a circular path of a radius of 60 millimeters in 4.3 milliseconds. Calculate the centripetal acceleration of the test tube. So, in order to calculate acceleration, we need velocity. First, we find the velocity. So we use the first formula that we went through, what we used just before. So v equals 2 pi r over t. R is 60 millimeters. Our period is 4.3 milliseconds. Okay. Once again, convert these into your centimeters and not your centimeters, into meters and seconds. Okay, so that's 60 times 10 to the negative 3. Yes. And that is 4.3 times 10 to the negative 3. Blah, blah. Alright. So, when we plug it into our equation, we have v equals 2 pi times 60 times 10 to the negative 3 over 4.3 times 10 to the negative 3. Okay. When you punch in your calculators, make sure you put this in brackets so that the calculator knows do this first, then do this. Okay. Alrighty. And that is equal to 87.7 meters per second negative 1. Alright, now we have a velocity. Now that we have a velocity, we can calculate our acceleration. So we go into the next formula. A equals v squared over r. Right? So our acceleration is equal to 87.7 squared divided by, and our radius is 60.0 times 10 to the negative 3, which equals 1.28 times 10 to the 5 meters per second, squared. Okay? So again, plug in your calculator as is, you're good to go. These are all pretty easy formulas to use. Right. So, motion diagram from an object undergoing uniform circular acceleration during complete revolution. Velocity vectors of equal length. Okay. So, we are looking at a full motion diagram, not just a velocity and acceleration diagram. So this is just velocity and acceleration. Now we're going to look at a whole full-on motion diagram. Alright, so we see when something is spinning around, moving in a perfect circle. In actuality, it's moving more like a dodecagon. If we were to draw it out, it comes out to a dodecagon instead of a circle, because it moves at tangents. Reason why I didn't go to art school. Okay, so we end up with something that looks like these instead. And these parts are the velocity. So the velocity is going around in tangents. We have an acceleration of equal magnitude going into the center of the diagram. Okay, so velocity is around the outside, moving at a tangent, and then acceleration is being pushed into the inside. Same magnitude though. So what you can do in theory is pull out a wedge, and you would have a diagram which can tell you the change in velocity between 2 points. Duck, duck, duck. Okay, says v1, negative v1, and v2. It's again more vector diagrams and drawing and all that good stuff. Okay, so that there would be a vector diagram of your velocity. Okay, and as we said before, acceleration, the arrow points to the middle. Okay. No, I'm writing that out. Anyway, so next, force causing centripetal acceleration. An object undergoing circular uniform motion has acceleration towards the center of the circle. So, looking at Newton's second law of motion here, for this one here. So, particle or object of mass moving at a constant speed around a circle or radius must have a net force pointing towards the center of the circle. It is a net force that causes centripetal acceleration of a particle or object undergoing uniform circular motion. Without the net force, a particle or object would move off in a straight line tangent to the circle. There you go. Think of those. I don't know if you guys have seen them before. They're like a merry-go-round type thing where you sit on it and you can push. Hold on. Let me find a photo for you. So you guys know what I am merry-go-round on. Playground. These things right here. These things of death. Okay, they work by using this force. So even though you're pushing it, it goes around, starts spinning, and you start creating a force that pushes the object into itself, so that way it's not getting pushed out. So when you spin something, there's a force pushing it out. So if you think, if you think of totem tennis, when you play it and you hit it, there is a force as the ball moves around in the string that pushes the ball outwards. Okay? To keep it level, there is another force pushing against it to stop it from flying off. Okay? To keep it an even force. So that's the forces that are keeping the centripetal acceleration constant. Okay, so magnitude of net force causing centripetal acceleration is calculated using F equals ma. But we write it, so instead of F equals ma, we write it as F equals mv squared over r. Okay, so it's written like this instead. Like, I'm pretty sure on your cheat sheet on your cheat sheet, on your equation sheet, you have F equals mv squared over r instead. So nothing new here. Force equals mass times velocity squared divided by the radius of the object. So if we're looking at example 1.4, where it has a mother pushes her 20-kilo child around a roundabout with a radius of 1.65 meters. Calculate the force required to push the child at a constant speed of 3.45 meters per second. Alright, so F equals mv squared over r. Velocity equals 3.45 meters per second. Our radius is 1.65 meters. And our mass is 20 kilos. Our force is our unknown. Okay, so F equals 20 times 3.45 squared divided by 1.65. If you plug that into your calculator, you should get the answer of 144 newtons. Remember, the unit of force is a newton. Should be a capital N, not a lowercase n. And so there's that. Now, there are also examples of 4 different forces that cause centripetal acceleration. Alright, so first we have gravity. Earth is spinning around the sun because we're spinning around the sun, and the Earth is spinning by itself. It sucks us to the center of it, which is why we stay planted on the ground. Next, we have tension. So think about the hammer throw or a totem pole. You're holding something, you have a string, it becomes taut, and you spin, spin, spin before you throw it off. Okay. Next, you have friction. So think about driving and going around curves, especially steep banks. And next is a normal force, causing the centripetal acceleration of a car moving in a circular dip in the road at a constant speed. Alrighty, and that is it. That's all for now. Alright. Hope you guys are going well with D&D. I will see you tomorrow for our single. Bye!